Recording is rolling. It is Friday, August 23rd. We're going to make the graphs for the car and incline lab from yesterday. And then next week, we're going into linear motion. Well, actually, you guys started linear motion yesterday. Today, we're really kickstarting this. I just, before I hit record, handed you guys this page. On one side has a bunch of linear motion puzzles that are algebra-based, so algebra-based linear motion puzzles. And on the opposite side are some graph type puzzles. Right? Now, I have not shown you guys how to solve these yet, but your guys' car and incline lab is going to lead to some equations so that you guys can solve those. Right? Right. So here you are. Here. Right, recap what you guys did yesterday. You guys had some Hot Wheels cars and some inclines and a bunch of tools and lab weights, and you guys are trying to figure out maybe something to do with this question here. What equation or equations could govern the motion of the car rolling down the incline? Right? So there was some fixed angle. Did you guys get about 5 degrees? If you got 4, 5, or 6 degrees, then you measured it correctly. Right? So that was fixed for everybody. That won't be a variable until a few weeks from now. Also, we're stuck in some gravity field. I forgot to mention that yesterday, but so that couldn't really be a variable. So that wasn't control for everybody. And then there were all these other variables. So maybe the mass of the car, what if it was more massive? How would that affect its motion? What's the relationship, the exact relationship between the rolling distance and the rolling time? Right? Like if it was double the time, would that be double the distance or would it be something different? How about the speed at the end? You guys had, where's my, you guys had these speed gates. Right? So as the car went through, you can see how fast is it? Was this thing going? Right? What did that have to do with either its rolling time or its rolling distance? Okay. So all those questions floating around. The best way to handle that, you guys figured it out. You guys told me, I think, was to split you guys up into different groups, and you guys each have to focus on a different facet of maybe this general question. Right? And we'll come together and put all these graphs together. You guys have this really open table. Right? So I was helping you guys a little bit, saying, finding the other example here. All right, well, I got this one ready to go anyway. All right, so I was looking for, you got different trials, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? You got variable unit, variable unit, variable unit. And what variables you need to put in these columns really depends on what experiment you were doing. Right? So here I've got mass of the car in grams, but it looks like I got that controlled all the way down. So that would not have been a variable for this particular lab, right? Maybe I've got different rolling times, different rolling speeds, right? If you had this version, maybe I should have also put a column for rolling distance. Maybe I should keep track of that too, right? But it depends on what you're searching for. Okay. So on the back of, the bump all. Okay, yeah, there you go. There's the 4 different experiments you guys had. Okay, we'll do it one at a time. We'll put these graphs together. Okay, so mass versus time, distance versus time, speed versus time, and speed versus distance. What would these look like? Okay, and then here you go. So on the back of your paper with the table on it, are these 6 graphs set up? Right. I really wish I had. If I could go back and do this again. I probably not label the axes and have you guys label the axes just to get the practice of saying like you guys see it's variable unit. Right? You guys see that? Like that. Okay, and then that's for AP, so don't worry about that. Right, so put all this aside. All right, let's get these graphs together. So the first graph we're going to do is mass versus time. You guys see mass versus time? I'll make mine really big. So looks better on video for you guys. Right, so this could be mass in grams. Yeah. Now, normally in this class, we're going to be doing kilograms, but today we'll just do grams. That's fine. And time in seconds. I can make a title for this graph. I'll call it mass versus time. Right, there you go. It's always like y versus x. Right, so mass versus time. Right? Oh, also graph rules. Like what variable should go on which axis? There are some rules for that. Guys, as a general rule, what tends to go on the horizontal axis? The independent or the dependent variable? I'm going to say independent. Yeah, independent variable. Right. But there's another rule that says if time is involved, if time is ticking along, then as a rule, you put that on the horizontal axis and that overrides the other rule. So that's why I have time down there. Right. So this was clubs. Guys, who had clubs yesterday? Who had clubs? All right, I'm gonna get some data from you. How about Alec? All right, what was the largest mass car you used yesterday? 450.7. All right, 450. I'm gonna scale this up to 500. Let's go 100, 200, 300, 400, 500. Right. So you probably have this graph already, but everybody else, you guys can make this graph right now. Right, good. So let's go 0, 100, 200, 300, 400, and 500 grams. Right? Oh, right. And then what was the longest rolling time you had?
6 seconds. 7.
Ah, all right. That's it. 1, 2, 3, 4, 5, 6. Oh, yeah. If it was like 6 or 7 seconds, then I wonder if that car had a lot of friction on the wheels. But we'll see what this graph looks like. No regret. All right, let's get some coordinates. Right, so I need to see a mass of a car and the corresponding rolling time. Okay. What's one coordinate? Like one mass and the corresponding time.
Johnny give you like one of the 450.7 maps?
Sure. Yeah. So 450 grams. So 450 grams. How long did that take to roll down?
3 seconds.
So 3.53. So 3.5. So I got bam, point on the board. I'll say 3.53 seconds for, you said 450 something grams. All right. So here's seconds. Here's grams. All right. So coordinates on the board. All right. All right. Let's get another coordinate.
Mass.
Sure. Yeah. Different math.
51 grams and then 3.4.
All right, 51 grams and 3.4 seconds. All right. So 3.4 seconds for 51 grams. All right. You have a third car?
3 grams and then 3.6.
3 point, right, so this guy right here. So 3.7 seconds was 83 grams. Okay. What else you got?
The same car.
Do you have a different mass car? Or
yeah, 232 grams and then 5.19.
5 point what?
0.19.
5.19. Right. So you got 5.19 seconds for 232 grams. All right. You have a fifth car? Or just this four? Right?
Yeah.
All right. All right. So, all right. I think we'll be able to keep this one up. Right. So, I think I had you guys hypothesize before you went to the library yesterday. What do you think this would look like? Like heavier cars. Is that going to make it sit down faster or slower, or would a fast car and a slow car tie with the race? Right. Now, based on that data right there, what do you guys think the answer to that question is? Like, as the car gets more massive, what's happening to the time? Yeah, it's about the same, isn't it? It's about the same, right? Could I call that like maybe no relationship? Do you guys think? Right? If I just flip the axes, this just becomes goes from horizontal to vertical, right? But horizontal line and a vertical line is kind of the same idea in physics. It's like if you change one variable, the other variable does not respond at all. Right? That's what we have here. You can change the mass of the car, and the time to roll doesn't really change. Okay? So it's pretty much a vertical line. Right? So maybe this guy's a little bit of an outlier here, but all the other cars, it looks like it was taking about 3.5 seconds to roll down, regardless of mass. A little tiny mass here, big old mass here, at the same time. Right, so, yeah, so it turns out that the mass of the car, the way the car, that's independent of how it rolls down. Right? Now the classic physics explanation has to do with actually back a little bit. Right? This is really similar to a famous experiment that Galileo did. He went to the top of the Leaning Tower and he dropped small objects and large objects off the Leaning Tower. Okay? Now everybody down on ground level watching these objects fall. Right? Which one do you think that they thought was going to hit the ground first? Probably heavy one. Yeah. And the reason they thought that was, well, Aristotle said that 2,000 years ago, and we've just been believing that for thousands of years. So that's probably it, right? But Galileo actually did this experiment. He dropped light stuff and heavy stuff. And guess which actually hit the ground first? Yeah, they tie. They did tie, right? So the classic physics one explanation goes like this. The larger object, yeah, it has more weight, has more gravitational force. It's heavier. Right? So, that one's gonna win, right? But it also has more, because what am I getting a sense of right now? Not the weight, but the mass or the inertia, the mass of the inertia, right? And it turns out that one's proportional to the other, so one effect cancels out the other. Yeah, and so they're going to tie. They both free fall at the same rate. So your guys' car on the incline is just a slowed down version of that same experiment. And so, yeah, and so the car is going to tie. Right, so mass is not a part of these kinematic equations because the mass and the weight end up canceling each other out. Okay. All right, so what I got next? Got some spades set up. All right, you guys ready to move on to spades? Spades? Okay, no, if you had the spades, we'll be able to get two different graphs out of those. Let's start with distance versus time, see what that looks like, and that'll kind of lead to the other one. So I'm going to set up some axes here. You guys are checking your paper. You want to volunteer your data here. All right, let's do so x versus t. I'll do rolling distance versus rolling time. Right? All right, who had spades wants to share their data? Who had spades? I saw Gianna first thing. All right, and so all right, might be different spades groups. And so what was your longest rolling distance?
227.
227. All right, let's go. 50, 100, 150, 200, 250. So 0, 50, 100, 150, 200, 250. Right, this could be in centimeters. Right? So there I got variable unit. Right, and same for time. I'll do variable, and the unit's going to be seconds. What was the longest rolling time?
3.45.
5. Let's go 1, 2, 3, 4. So 0, 1, 2, 3, 4. All right, let's get some coordinates. So what's one coordinate?
Right, 227, and then 3.45.
All right, so about there, bam, bam. All right, so 3.45 seconds to roll 227 centimeters. All right, what's another coordinate?
3.06.
Ooh. Got it there. 3.06. All right, next coordinate. 3.3. All right, next coordinate.
100 centimeters, 3.6.
6. All right. Do you have a fifth car?
Yep.
All right.
50 centimeters and 1.52.
All right. So 1.52. All right. First, these are seconds, centimeters. All these numbers, of course, have units attached. There you go. Okay. Yep, that's about what that should look like. Yeah, yeah. All right. So looking at those points, maybe I'll throw in sort of a 6 point, which is, guys, if it's been rolling for 0 seconds, how far is it rolled? 0 centimeters, right? Starts at 0, 0. Right? Can I kind of logically figure out that 0, 0 should also fit on the graph too? So if I throw that on, and maybe this makes this even clearer. Right? Guys, what relationship does that look like? Parabola? You guys think of parabola? Right. I think it's probably going to be a parabola. Right. That's what I would suspect. Right. There might be some good reasons to think that too. Right. But yeah, I think it's going to do about like that. Right. I think that's the best fit curve right there. Right, you guys think? Sure. Yep. Okay. So suppose I suspect a parabolic relationship, but maybe I don't know for sure. What if it's proportional to time cubed, or what if it's not exactly a parabola, but it's a little bit deceptive, maybe? Right? So we could test this the same way you guys did the other day with, you guys remember circles with radius and area? This is going to be pretty much identical to that. So I suspect this. I think the distance it rolls is proportional to the time squared, which would be a parabola. Right, that's what I suspect. Kind of like, here, draw this from your lab from the other day. Right? You guys had a circle with a radius, and if you said what's the relationship between the area and the radius, that was also a parabola, right? But then we made another graph that was not area versus radius, but area versus radius squared. Because if I square the radius, that's that physical square. and I say, what's the area of the circle to the area of that square? And that was a direct relationship now. Ooh, so all the points line up in a straight line, right? I think if I do that exact same trick here, that can tell me for sure if this is a parabola. Not only that, but we can whip off the slope really fast and get in the exact equation really fast. So I'm going to do x versus t squared. So let's do distance also in centimeters. And as a function of time squared, guys, what do you think the unit is for time squared? Square seconds. So second squared, right? It's a little bit abstract. Like radius squared, that's easier to see. That's like a physical square. But square seconds, okay, you have to think a little bit abstract. Okay? Right, so let's, okay, I can just copy paste the vertical axis. 50, 100, 150, 200, okay, that can be the same. 0, 50, 100, 150, 200, 250, boom. Okay. Those are all, of course, centimeters. All right, now square seconds. Well, see, 4 squared 16. It'd be like 5, 10, 15. How about that? 0, 5, 10, 15. Okay. All right, so boink, 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 boink. Very good. So I think I can figure this out. So square all these times. So 3.45 seconds, and then square that. I'm gonna get 11.9, and that would be square seconds. So 11.9 square seconds is going to correspond to 227 centimeters. That's right about there. Okay. So 11.9 227. So square seconds in centimeters. Okay. Next one, if I take 3.06 seconds and I square that, that's 9.36. So 9.36, 190, boink, boink. It's right about there. Okay, 9.36, 190. Okay. Next one, say 2.6 seconds, square that. That's 6.76. So 6.76, and then 100. Right about there. 6.76, 100. But 2.3 seconds, square that. It's 5.29. 5.29. Okay, 5.29. Okay. And then, oh, did I write? I wrote something wrong. I'm sorry. Johnny, can you tell me again? I wrote a number down wrong. Which one?
1200.
This one?
Yeah.
What should it have been? 150? Oh yeah, that looks better. Yeah, thank you. 150. 150. All right, so that actually goes way up here, doesn't it? 150. Yeah. Oh yeah, okay, that looks better. 150. 6.76, 150. All right, thank you. 100 was 5.29. It's more like back here. There we go. Right, so let's get rid of all this. Right. Yeah, 5.29, 100. There we go. That was good. Right, and then see 1.52. And square that. It's 2.31. 2.31. That's 50. Boink, boink. Okay. 1.5. Why did I do that? 2.31. 2.31. And then 50. Square seconds. Centimeters. Yeah. Okay, that looks pretty good. Looks pretty good right there. Maybe you can kind of logically figure out 0, 0, which should also fit there. Okay. So, curve of best fit. Is that a direct relationship right there? Guess that. Okay. So yeah, remember a few minutes ago I was suspecting this was probably parabola x proportional to t squared. Right now we've pretty much confirmed that. Yeah. Okay. Oh, let's get an equation for this line. Can I pick 2 points on the line, get a slope? Right. Just the fast way. I'm gonna pick the origin and this point here because they both pretty well on the line. Okay, rise over run. Can I do that rise, divide by that run, get a slope? Okay, let's get a slope. So that's gonna be 227 centimeters. So that's the change in x. And then the change in t squared is 11.9. So rise over run, that's 19.07. Yeah, I'll call it. Let's just round that to 19. 19.07 is about 19. Okay. So now I can come up with this governing equation for the distance the car rolls as a function of time. Distance it rolls is equal to 19 right? And there's some units. We're gonna leave a little space there, and then times t squared. Okay. And I left the space to write the units in because most of you guys can figure out the units on this number. It's 19 something. Guys, it's 19, and what's the unit? Okay, I need a centimeters per what? Second squared. Exactly, right? Because here's two different ways to reason why that would have to be the case, right? If I do rise over run, the rise is in centimeters, the run is in square seconds. There's a slope right there with the units, right? Here's another way, is what if I go plug in numbers into this time? Like, guys, if this car's been rolling for 1 second, how far did it roll? 19 centimeters. Because I plug in 1 second, I square that, just the square seconds and square seconds cancel out. And there is a unit left on the board, and it's just plain centimeters. Guess that? Right. What about this? What if the car's been rolling for 2 seconds? How far did it roll? And don't say 38. Guys, what's 2 squared? 4? 4 times the original, 4 times. And then 4 times 19, is that 76, I think? Right. So what I'm getting towards here is a proportional relationship. You're going to see this a bunch of times throughout this class. Is whenever you see this, especially like a parabola, you'll see like a squared proportion. So if it's been rolling for twice the time, that's going to correspond to 4 times the distance. See if you guys can do another proportion. What if it's been rolling for 3 times the initial amount of time? Guys, 3 times the time is how many times the distance? What's the factor of 3 squared? 9. 9 times the distance, right? You guys said 3 times the rolling time is 9 times the distance. That's also this. And that equation also applies to this graph on the left side. It's also x equals 19 centimeters per second squared times the time squared, right? The same equation can describe both of these graphs, but they're on different axes. So that's why they look like different graph shapes. Right, guys good? Good. Right. And to round this out, next week we're going to apply these 3 kinematic formulas. And you guys basically derive this first one. If it starts from rest, then initial velocity 0, that goes away. So the rolling distance is, you guys see, it's proportional to the time squared, right? We'll talk about the acceleration is the rate that it's speeding up. Right? We'll talk about where the 1/2 comes from about next week, but basically that. Right? Now, if you give the car a push, that's where this other term's going to come in, right? So you guys more or less derive that top equation just right now. Right? All right. Okay, guys ready to move on? Next set of graphs. Let's go into diamonds, which was velocity versus time. We're going to do velocity versus time. Do velocity, so final velocity. So velocity car going through the finish line versus time. So velocity, final velocity versus time, right? Okay, so who had diamonds? Who had diamonds? All right. So how about Evan? Evan, what was your longest time?
Or longest time?
Yeah.
2.67.
All right, let's go 1, 2, 3. So 0, 1, 2, 3. And what was your fastest speed?
Fastest speed was 135.03.
135. Okay, so that would make this centimeters per second. This, of course, is going to be in seconds. You said 135. Let's go 25, 50, 75, 100, 125, 150. That's 0, 5, 50. 100, 1.5. All right. So I got variable unit. I got my number scaled, starting from 0 scaled linearly. Right, so speeds in centimeters per second, times in seconds. Right. Let's get some coordinates. So what's one coordinate?
1.71 and 95.4.
1.71, and you said 90 what?
95.4.
95.4. So 1.71, 95.4. Okay. So this be in seconds. This is in centimeters per second. All right, we got one. All right, what's the next coordinate?
2.27 and 118.7.
2.27, and you said 118.
76.
118.76. All right, next coordinate.
2.67 and 135.3.
135. All right, you have a fourth car?
Yeah.
All right, okay.
1.35 and 66.
6. Right. And you have a fifth one? Okay, so those 4. All right, actually, yeah, that looks pretty good. That's pretty good. Right. Do you guys think it can logically fit in also after 0 time? It's picked up to how fast? 0 centimeters per second. That's starting from rest. Initial velocity is 0. You release the car from rest, so that could be a point also. And guys, what relationship do you think that is? Yeah, direct relationship, linear relationship. Right. That's to say, if the car's been rolling for like double the time, it's picked up to double the speed. Or triple the time, it's going to be triple the speed. So that could be zip. Oh, that's pretty good right there. Do you guys think? Pretty good. Right. Line of best fit. Right. Oh, yeah. Now this point's really close to being on the line, and the origin I've got also. So I'm going to play off those 2 points and come up with a slope, rise over run, and then I'll be able to get a governing equation for what is the speed of the car as a function of rolling time. So rise over run. This is 135 centimeters per second picked up to, and about 2.67 seconds. Okay. Actually, this number on my screen represents an acceleration. So I'm going to say the velocity it picks up to is equal to 50.6. That's going to be centimeters per. Guys, what's centimeters per second divided by seconds? Centimeters per second squared. Sure is. Right. And that's all times the amount of time in seconds that have passed. There you go. There's your governing equation. That's the equation of that line. Right? Right. So see if you guys are following. If your car was rolling for 1 second, it's picked up to a speed of what? Yeah. 50.6 centimeters per second. Right? Because one of the seconds cancels. Centimeters per second. What if it's been rolling for 2 seconds? How fast? Yeah, about 101 centimeters per second. Okay. Okay. Guys see that? So we're doing on time here. We've got 46. All right. All right. Let's. You guys ready for last set of graphs? All right. We're going to move on to hearts. So this is going to be speed as a function of not time but rolling distance, and we'll be able to get 2 graphs out of this. 2 graphs. So let's do V final versus X. So put V final here. Put X here. Start with that. Who had hearts? Who had hearts? All right, go ahead, Carson. What was your longest rolling distance? 200 centimeters. All right, so let's go 50, 100, 150, 200. 0, 50, 100, 150, 200. All right, and what was your fastest speed?
150.
Before, let's go the same. 50, 100, 150, 200. So this could be in centimeters per second. This would be in centimeters. Centimeters. So 0, 50, 100, 150, 200. All right, let's get some coordinates. What's one coordinate?
200 centimeters.
6. All right, so you got 200, 154.6 centimeters per second. All right, what else you got?
100 centimeters and then 108.6 centimeters.
Okay, 100, 108. All right, what else?
75 centimeters and then 94.6 centimeters.
94. All right, you got 75, 94. All right, what else?
50 centimeters and then 74.3 centimeters.
50, 74. All right, you have that fifth one?
25 centimeters and then 51.6 centimeters per second.
All right, so 25, 51. All right. Point. All right, so there you go. And then probably logically 0, 0 could be point 0. Rolling distance, 0 speed is picked up to. Right. Guys, what relationship do you guys think that is? Square root. Looks like a square root. Okay. That would be my, yeah. I would suspect that's gonna be a square root. Looks like a square root, doesn't it? Okay. Now, if I suspect that velocity is proportional to the square root of the rolling distance, I could do some algebra right there. I could square both sides. I could say, well, that also means velocity squared would be proportional to x if that's true. Like if one is true, the other is true. Just they're an algebra step away. Okay. So that's the next graph I'm going to do. Let's do velocity squared versus rolling distance. So VF squared, that's going to be in centimeters per second, and then square that whole unit as a function of x in centimeters. I can just copy paste to, how are we doing? We got 21. No, hold on. 56. Yeah. Okay. 50, 100, 150, 200, 50, 200. If I square each of these, see what's 154, 6 squared. Okay. B. Okay, so the numbers are going to be really big. That's okay. Let's go 0, 5,000, 10,000, 15, 20, 25,000. 5,000, 10,000, 15,000, 20,000, 25,000. So 23, 9, 23, 9 is 200. There we go. So at 200 centimeters, it was 23,900 centimeters squared per second squared. Funny looking unit, like abstract line there, right? But these other ones,
Wait, what's the Y value?
23,900. Okay. Okay, what's 108 squared is 11,664. So 100, so 11,664. So 100, 11,664, something like that. Right. What's 94 squared is 8,800, 75, 8,800. It's got 75, 8,800. What's 74 squared? 500. So 500. Got 50, 5,500. Right. And finally, 1 squared, 600, 346. Yeah. So 25 and 2,600. All right. Ooh, guys, does that look like a direct relationship? Zip. Sure is. Sure is. That is exactly what that should look like. So yeah, in fact, that is true. That velocity final squared is proportional to x. And you could get an equation out of that too. I'll show you guys kind of where this is headed. Oh, I think let me back up to the last graph. I forgot to show you guys this. This right here, the last one we did a few minutes back, is basically this here. Okay. If the car starts from rest, V is equal to AT. If you give a car a push, point, you got that. Okay. The one we just did right now, actually just paragraphs because they're the same idea, just on different sets of axes. Okay. Is this last kinematic equation we're going to use next week. Okay. So if the car starts from rest, the initial velocity 0. You can see the speed squared is proportional to the rolling distance. That's what you guys just did. Right. We'll talk about the 2A more next week. Okay. All right. All right, there you go. Right, so once you guys have, okay, you should have all your lab data from yesterday. Okay. You guys have the 6 graphs. If you have the 6 graphs completed, double check, make sure your name's on your paper. Your name's on your paper. Turn that into the grade tray. Here's the grade tray right here. Turn it to the grade tray, and then I will get you guys points in the grade book. That is a wrap on the week.